Believe it or not, fine-tuning an LLM with your own data doesn't have to be hard or expensive, and we're going to discuss and demonstrate a really simple process that is by far our favorite way to fine-tune after over a year of working with different available methods. This also happens to be a very low-cost option. Now, when you're fine-tuning models, Hugging Face is going to be one of your best friends. You're going to use Hugging Face libraries, mostly to be able to download base models, tune them, and even do some engineering around the fine-tuning process. When you go to the Hugging Face Hub, you're going to find the models that you want to fine-tune. In today's demonstration, we'll be using the Mistral model. However, as a layer on top of the Hugging Face Hub and libraries, we'll be using a magical library called Unsloth. This enables a brilliantly simple fine-tuning experience, including incredible unmatched memory efficiency to avoid OOM errors or brittle and expensive multi-GPU setups. Not only that, we'll use rope scaling to give you an effectively unlimited token context window. We'll be running this on Colab. Oftentimes, your model, context window, and dataset can fit in the free tier of Colab with a single T4 GPU. However, worst case scenario, it's a relatively cheap and easy upgrade to a single A100, which has been able to handle our hardest fine-tuning scenarios flawlessly. Unsloth is a pretty small company, just a couple of Australian brothers who want to democratize LLM fine-tuning. Let's head to their public source code, and there you'll find a notebook for Mistral fine-tuning. While this will be core to our process, we'll need to do data preparation work beforehand, customize this notebook, and walk through some end-usage inference considerations. Among other things, we'll help you prepare your own data for the fine-tuning rather than having to use an existing public dataset from Hugging Face. Ensure you're logged in with a Google account and then proceed to connecting to a T4 instance, which is a free GPU option in Colab. There are ways to calculate if you'll need an upgrade to A100, but honestly, we find it's just quicker and easier to try out a T4, then shift to an A100 if you run into issues. Anyway, before we actually get started with the notebook, we need to prepare our custom fine-tuning data. I'll shift over to an IDE where we'll set up a data preparation script and directory of training data. We'll then plonk some example text files into our directory, noting that we've done absolutely no pre-processing. Our fine-tuned model aims to summarize short stories in a specific personal style. These simple TXT files can potentially hold a significant amount of text. Again, we'll be able to handle any context length via rope scaling. We get the best results when fine-tuning with at least 100 to 200 examples, but are reducing that significantly just for the sake of quick demonstration. So we just need to bring this data into a couple of line-delimited JSON training files for compatibility with the fine-tuning process. Upon intake of those files, we'll see some interesting token counts, like this 18,000 token count for one of our short stories. This tells us that we'll need to choose a relatively large context window when fine-tuning this model. However, that additional context does come at a bit of a computational and quality cost, so we don't want the window larger than we need. Let's keep the ball rolling and prepare our training files, which is really just the final step. We're looking at a few dozen lines of Python here, and most of it is just reading and writing to files. And look at that, we now have all of our data neatly arranged in these line-delimited JSON files. With that squared away, let's revisit our Colab notebook and connect to our T4 instance. Once operational, we'll get down to business. A few changes will be made as we progress, but you're safe to execute this first cell. Moving ahead, there are a couple of tweaks to consider. Most importantly, we must alter this max sequence length. Thanks to rope scaling, we can support any context length. Typically seen in multiples of 512, our sweet spot, based on that table of token counts from earlier, is probably around 24,000 or maybe 32,000 tokens, giving us a bit of buffer beyond the largest existing story. Additionally, using the instruct Mistral model, as opposed to the base Mistral model, offers a bit more of an opinionated and capable foundation. This might be a worthy swap. We're implementing a 4-bit quantization to minimize memory usage and training times. Don't forget, we can utilize resource monitoring to keep track of our GPU, RAM, and disk space. So far, everything seems to be in order. Next, we may need to tweak the R value in this notebook. It's set rather low to reduce computational complexity. However, the QLoRa paper recommends an R value of 64 and an alpha value of 16. They suggest that these values generalize quite well. A higher R is tied to more computational complexity, but it can improve quality. The alpha value is essentially how much weight we give to the fine-tuning data. Anyway, we'll adjust these values and adopt the QLoRa paper recommended values over the notebook's default ones for a more production-grade model. Next, we need to tweak the data loading. Let's ensure all these training files are available in our notebook, then fix up the dataset code to use that data. This piece of code here is our templatized prompt, assembling the instruction, input, and output together. We'll then use this as a text field for training. As for the batch size argument, we can remove that. Let's see if our newly created dataset works as expected. Everything's grooving, so we're moving. We might need to switch up a few gears in the training code here. First, notice that the max steps are set pretty low. We'll want to increase this so you can see where the loss starts to plateau for our fine-tuning. With a demonstration dataset of 5 examples, we'll hit that point quickly, but if you have a dataset with hundreds of examples, you'll probably want this to be in the 500 to 800 range. It's also a good idea to have a save strategy. Consider saving every 25 steps in case you find, for example, that the 225th of 300 steps is the sweet spot for your model. This gives you the freedom to pick any milestone in the training and use the model at that checkpoint. We want to minimize loss, but without overtraining. We've got an error of some kind. Let's examine our dataset once again. Looking over our text value in the dataset, it seems to have a problem. Aha! We simply need to brush away that bit of extra code that lingered from before. Let's give our dataset setup another shot. All right, now we're cooking. That's looking great. Before proceeding, let's check our GPU, RAM, and disk usage. Our T4 GPU is running up against its 15 gigabytes of memory, so we may need to increase the memory with a different instance type. A100s are the best way to step up the resources. Enabling the A100 setup means a restart of the runtime, so we will of course have to reintroduce our files, and then it's just zip zap zoom rerunning our cells. The T4 may very well work for your use case, but it's a quick upgrade if necessary. and it looks like this accelerator will work well for us. We'll be compiling our table of training steps and losses shortly. If we sneak a quick glance at the Resources tab, we can see that we're using about 26 gigs of memory, which gives us plenty of breathing room on this GPU. As our training grinds on, we'll be able to keep tabs on the loss across the training steps. The training is wrapped up, friends. We can now sift through the loss metrics here and quantitatively assess if and where we want to use a checkpoint. As pointed out earlier in the video, the sweet spot will be super early in our demonstration with just 5 examples. Ideally, you should have at least hundreds of examples, which should give you a sweet spot in the hundreds of training steps. I know the sweet spot commentary is a bit wishy-washy. Feel free to plot the loss if you want to be a bit more precise. You're looking for where additional training steps are having much less impact on the loss reduction, but you don't typically want to select the absolute minimum loss. That would likely be overtraining. Looks like our loss starts to level out somewhere around 50 steps. Now, of course, you don't want to train this fine-tuned model every time you need to use it, so let's talk about saving and using the model. The notebook suggests saving just the adapter layers, and indeed that'll be a bit faster save. However, we recommend saving the full model with Float 16, enabling easier inference setup and a more standard saved model format. Are you ready for the big reveal? Let's switch this to true and demonstrate how to push to the Hugging Face hub. For the designated user, we'll use our demonstration demo user. For the model name, let's do Mistral 7B summarization Q LoRa. For the token, let's hop into our Hugging Face account, into the settings, access tokens, and create a new access token. A quick email verification and refresh of the page later, we're ready to create this new token. Token in place, we can publish this model publicly by running the cell. Use the private argument if you want to save this as a private model. All right, let's now imagine we're in any other notebook, script, service, or application and need to use this model. There are a variety of ways to do this, with VLLM being the standard for production APIs, but we'll show the Hugging Face Transformers path. First, we set up our tokenizer for preparing our input text. And just for succinctness, let's grab a portion of our test story here, maybe just the first paragraph. When we're setting up the inference, we will use the max length values that we had from earlier. So let's scroll to the top here and snag that value. And there's our summary. Furthermore, the training and inference combined have only ran us about $2. We'll provide the diagram here as well as the Python code in the video description. Also, as part of our AI tutorial series, we'll be donating $1 for every 10 new subscribers to this video to the Center for AI Safety. So, if you'd like to support the great folks working on AI safety research, as well as the channel, please consider subscribing. Thank you so much for watching. We'll keep an eye on the comment section for any questions, and please enjoy responsibly.